Okay, so what am I going to talk about this year? What I'm going to talk about this year is a continuation of a couple of things that I've talked about in previous years. I'm going to pick up on both of the talks that I did last year, one of which was on unit testing, what we talk about when we talk about unit tests, and the other of which was on the central and fundamental topic of FizzBuzz. I will be continuing that this year. And I'm also going to hark back to a talk I did a few years ago here, functional programming you already know. Now, this talk goes a little bit beyond and within each of these, which also means that some of the slides are new. If you spot a bug on one of the slides, there's a possibility, there's two possibilities. One, it's intentional. Two, you've misunderstood it. Or three, it actually is an error, just like my counting there, okay? So if it actually is in the third of the two options, please let me know, because that's the only way that you actually find bugs on slides, is by projecting them to people. You can stare at them for hours, but the minute you put it in front of an audience, something happens, okay? Now, I did actually, there's this expectation that I am going to always at some level or other talk about singletons. And I did actually promise in a tweet that there would be a singleton. And here it is. We are done, okay? That's not your singleton, that's my singleton, okay? The joy of clearing out your office or rearranging your office and discovering that you've actually got enough named stuff to form a sentence or a reasonable phrase. Okay, what am I going to actually talk about? It's an observation from Tim Berners-Lee here, and this was kind of the design principles for the web. And he wrote this in the early 90s, hence why the first paragraph is sort of time anchored. Computer science in the 1960s to 80s spent a lot of effort making languages which are as powerful as possible. Had he written that in the early 2000s, he would have changed 80s to 90s. Had he written that in the early 2010s, he would have changed that. You get the idea. Nowadays, we have to appreciate the reasons for picking not the most powerful solution, but the least powerful. The reason for this is that the less powerful language, the more you can do with the data stored in that language. There's this idea that we've got this idea of like, increase the power. You know, you can become omnipotent, okay? You can become omnipotent within the code. The trick here is obviously something has to be omnipotent, but maybe it's not the bit you think it is. Maybe you need to leave the clever stuff to something else, or allow the opportunity for something, have a very simplified form of representation, and optimize and organize around it. So he said, if you write it in a simple declarative form, which he mistyped, anyone can write a program to analyze it in many ways. And there's that idea. Let's actually, I will correct his the incorrection. There we go. Live updates. So the idea here is the declarative approach is in contrast to the imperative approach. The imperative approach covers a great many paradigms and languages. The declarative approach, likewise, perhaps fewer, but we don't always recognize the language. So, for example, I dug this one out. This is a printout of Feldman's original make paper. As you can see, I've used a portable document format to store this on. He wrote it in the mid-70s. And make is interesting because it's one of the kind of classic family. We always think of it as build tools, but we often forget that there are a number of tools which are around the periphery of our programming skills that we don't recognize as first-class programming languages. And the observation made in the sink of all human knowledge is the makefile language is similar to declarative programming. There's the idea that this class of language in which necessary end conditions are described, but the order in which actions are to be taken is not important. It's sometimes confusing to programmers used to imperative programming. There's this idea that what you're doing is you are stating some kind of intention. You say, this is where I want to be, okay? You figure out the details. Oh, you can give it a hand. Obviously, there's a sliding scale. We don't just say there is imperative and there is declarative. There is a sliding scale. But the idea is maybe if we move over towards intent. If you've ever tried to write a build file that is strictly imperative, you kind of fall asleep after a while. It's very, very boring if this file is older than that file. Eventually, you end up reinventing a declarative form because you start seeing the regularity. You say, look, there's a bunch of files here. I want to talk about their dependencies. I don't actually want to talk about the mechanics. Now, obviously, this has a very strong relationship to a number of other things. We deal with markup languages. It turns out that sometimes we are confused by these things, but they're all over the place. Backus now form. This is the BNF for JSON. Okay? We see BNF all over the place, and to the point that people get so attracted to this as a way of defining language that we've ended up sort of saying, you know, it'd be really cool if in my code I could do that. So you've got something like Boost Spirit, which allows you to do this direct rendition. Now, this gives us kind of a bit of a realization. If we revisit Nicholas Wirth's proposition, he wrote a book entitled Algorithms plus Data Structures equals Programs. If we look a little more closely, actually it kind of tends towards this. There's a lot of desire to move it towards this. And perhaps we should kind of acknowledge that and just see where that takes us. And this is also not news. I mean, if we go back to sort of fairly timeless classics, most things ultimately Fred Brooks said at some point or another. There's a fairly good guarantee. You can kind of pick a random quote, and if you can't attribute it, let's just say Fred Brooks. Okay? If it has the air of timeless knowledge, and particularly if you've got stuff like this, and he's got a whole section, representation is the essence of programming. And we could actually go a little further and drop out the essence of, if we're going to really make the point a little more strongly. Representation is programming. But also, if you have that kind of timeless feel, how do we know something's timeless? Because it sounds really old. Show me your flowcharts. Flowcharts. And conceal your tables, and I shall continue to be mystified. Show me your tables, and I won't usually need your flowcharts. They'll be obvious. Now, that might be overstating the case. I've certainly seen sort of quite a few things that made me utterly mystified. You're doing what with your tables? And perhaps the most common form of table is the spreadsheet, and that may work against us with the realization, as Simon Peyton-Jones observed, Excel is the world's most popular functional language. This may be a good thing, it may be a bad thing. I'm not entirely sure. A few drinks, I'll let you know, okay? But it's definitely a thing. So when we're talking about imperative and we're talking about declarative, what does that mean at the code level rather than what he's talking about here, the architectural level? I'll pick on some Python code. Get a sense here of where our attention is being drawn. Your attention is being drawn. OK, so what I'm going to do is I'm going to create some squares. OK, squares, we're going to initialize that to an empty list. We're going to initialize a loop counter to 1. Actually, I'm reading ahead, aren't I? I'm going to initialize a variable called squares to be an empty list. I'm going to initialize some variable I to be 1. Whilst I remains less than 101, I will append the square of I to that list, and then I will increment I by 1, and I will keep on doing that. What I've done here is utterly failed to describe my intent, unless your goal was actually to write a loop and to declare. Your goal is to declare 2 variables, write a loop, and populate one of those variables with a list that happens to be the square of the numbers from 1 to 101 using the other variable. It's very rare that you're ever going to be given that kind of brief. Okay? There's a good reason for that. You have to learn. Is that for me, John? No. Is that for me? Yes, Kevlin. Yeah. Is it? Yeah. Yeah. The goal here is that one of the things that you do with programming, you don't even notice you do it. You read past some of the mechanics. You get so practiced at ignoring loops. The more experience you have in programming, the better you are at not seeing loops. Okay? Because you've seen them all. Is there any kind of loop you have not written? Have you written enough loops in your life? No, I need to write more. Okay? Well, I'm going to do it again. I'm going to loop the act of writing loops. The point here is that it is itself repetitive. And there are classes of loops we already know about. There's nothing to be gained by repeating them again. We've got loops to find things. We've got loops to apply things. What you do is you learn what these things look like, and then you try and find the meaning within it. So maybe I'll do something a little more Pythonic, which is a little more declarative in terms of moving closer to our intent. I've still got squares initialized. But what I've done here is, yeah, there's still another variable called I, but I bound it to the loop in such a phrase that I don't have to sit there and go, right, the increment and go and hunt it out. I've bound it to the loop. I basically said, look, there's a thing called a range. I'm not merely incrementing numbers until they hit another limit. I've got a concept of a range, and I'm going to traverse that range, and then I'm going to append. And then you've got the idea here, which is this anchors you properly. It's just like, look, we know about loops, all right? We're pretty good with loops. Here's an idea. What I'd like is a list. And I'd like a list to be populated with squares of the numbers from 1 to 101. You can pretty much read that off there. And it's also, if you ever try and explain this to a child, it turns out that this version is actually easier to teach them than the previous versions. Because in the previous ones, you have to keep sitting there and setting up state and mechanics and telling them we're going to do this, then we're going to change that. And it's only our years of experience that prevent us from seeing the fact that this is actually the simpler starting place. And that the correct way to present this code, if you want to tell somebody this is what your machine is doing, is you start here, then you do this, and then you go back to this. That's the correct way to present this example, the other way around. So what we're dealing with here is an idea that we find in set and logic, an intention. Now, this is slightly different spelling to the spelling that you may be used to, although I'm always wary of saying this to programmers whose spelling skills are not perhaps the best in the population. It's always worth pointing out that in software development, we invent things to compensate for our inadequacies. Okay? So there's the reputation that programmers aren't very good at communicating. That's why they invented email. Okay? Who wrote the first spell checkers? Yeah? Where did that demand come from? Yeah? Right, exactly. So, but I will tell you that this is an unusual spelling of it. It's the less usual. And intention, the set of characteristics or properties by which the reference of a given expression is determined. And so on. Right. For example, the intention of prime numbers may be having non-trivial integral factors, whereas its extension is something more explicit, 2, 3, 5, 7, and so on. Okay, the idea is define the property, and what we're going to do is we're going to define a class of things like that. And we have this idea of an intensional expression. So here we've got the idea of a set intension, or a set builder, or a set comprehension. I'm going to take the numbers, natural numbers, such they lie in the range 1 to 100. I'm going to give you the square. Now, it turns out that we've actually seen this all over code in various forms. Select from where. This is not a coincidence. We kind of keep re-importing and reinventing this idea. It's very familiar. This is how you understand comprehensions and, indeed, large amounts of code. This is a very simple declarative idea. I want these things. This is where I'm getting from, and this is what must be true of them. I'm sure there are loops involved. I'll leave that to you. Okay? You push that somewhere else. You let somebody else take care of the loop. Outsourcing, very popular. Okay, so this idea, list comprehension, is a construct that is based on the set builder notation. So if I switch to Haskell, we take something fairly similar. We take, obviously, we can define the ordering, so therefore it's going to be a list rather than a set. And we say, right, I'm going to populate this, x squared, take x from 1 to 100. I don't have to sit there and labor the point, that little dot notation. It's kind of useful. You know, people thought about it in the 1960s and then kind of forgot about it a couple of decades after. It turns out the idea of actually being able to say a range of numbers is really kind of common. The fact that we have to start using words like range or add things to libraries to generate ranges constantly surprises me when I look back. Did we not know that there would be ranges of numbers when we set about coding? Is this news to us? So there's a kind of a curiosity there. So we're going to take that, okay? And that's going to give us all kinds of useful stuff. Okay. But all I've done there is I've defined the squares of the first 100 numbers. This one's going to keep you busy. Okay, I'm just basically going to say, oh, no, it's just going to be positive numbers. I'm just going to say, yeah, anything 1 or greater. And, you know, this is great because there's a mathematical statement. This defines a certain truth. And if you've got kids, at some point your kids will have asked you, you know, what's the biggest number? Or they will say, I've got a really big number. Dad, is squidillion a number? Well, how big would you like it to be? You know? And I taught my kids about Google, so they said, oh, what about 2 Googles, Dad? 3. Oh, damn. And so they will start asking various questions, and we've got an infinite number of things here. And so it's, well, yeah, that's great. That's maths for you. Well, we can't do that in code. No, we can't do that in code. Oh, bugger, we can. It turns out that we can, and that's not a problem. So here I am in Haskell saying, what I'd like is squares from 1 to infinity. Get going. Now, there's a very simple point about this one, is that what we've simply done is we've stated declaratively our intention. The problem is that all too often when we look at an expression, we are expecting that expression to be evaluated. It's very difficult, depending on your language background, it's very difficult to look at an expression and not evaluate it. You're doing it in your head, just, okay, I don't know how far you've got, but... okay, but we're doing it in our heads, we don't even know we're doing it. But you've got to take a leaf out of the mathematician's book. Be lazy, be really lazy. Okay, this is why mathematicians sort of do various things like saying, oh, yeah, it's trivial to show that. I cannot, it's hashtag I cannot be bothered. It's just like, yeah, oh, and it just applies, and yeah. So there's this idea of lazy evaluation. And the idea there is, if you want to deal with infinities, this is perfectly acceptable. You don't need cloud storage. If you want to deal with infinities, just don't look at infinity all at once. Okay, that's the trick. If you try and do it all at once, that's going to be a problem. But if you look at it one element at a time, then you're okay. Okay, it's up to you to decide what your boredom level is. And then you can say, well, actually, no, I understand what my attention is. I can take that. In fact, what I'll do is I'll take 100 of those, thank you very much. I'll take the first 100. I'll have the first 100 of that, at which point we now actually care about it, and now we can evaluate it, because we've actually said something meaningful. I'll take the 100 of that and go through. I was asked, I used this slide the other day, or this example the other day, with somebody, and they said, well, what gets evaluated? I said, well, to be honest, you're never going to get a list of 1 to 100. You will get a list that goes 1, 4, 9, 16. That will take up storage. But the idea of a list of numbers that ascend in steps of 1 is kind of easy enough. You don't actually need storage for it. It's a bit of a waste of storage. But you know what? Because we haven't specified that, the runtime is free to do that. It's free to say, oh, I know this is counting. Yeah, we're good with this, okay? We're computers, right? We can do that. We don't actually need storage to do these numbers. Okay, so that gives us sort of an initial flavor of this. But let's take this to something, a real application. FizzBuzz. As was observed, FizzBuzz was invented to avoid the awkwardness of realizing that nobody in the room can binary search an array. We'll get to binary search later. If you're not familiar with anybody not familiar with FizzBuzz? Okay, see you in the bar later. It is a drinking game, although if you go to the Wikipedia page, it will tell you that it's a children's game for division. This is news to me. But it also says sometimes it's an adult drinking game, citation needed, which I think is very funny. And the idea simply is that you are going to count from 1. The idea is normally it's set as a programming task or a coding kata. Count from 1 to 100, and you count off 1, 2, fizz. Anything divisible by 3 is fizz. 4, buzz. Anything divisible by 5 is buzz. Fizz, 7, 8. If I say 9, I'm out of the game, or I take a drink, okay? You see, I have no idea what kids' incentive is in this, okay? And actually, my youngest son loves playing games, and he loves word games and numerical games and so on. And we did this on a holiday recently. We were waiting for something. I think it was food. We were in a restaurant, and we tried all the other games. And I said, oh, why don't we play FizzBuzz? He said, oh, yeah, I know how to play that. You know, when you've got sober people, it's really boring because you are totally there. It's just like, yeah, okay, I think we're going to give up because this is actually boring. Counting sheep would have been more exciting. So, not the world's hardest programming problem, but apparently it's really important. So here's a fairly imperative implementation of this in Python. And we can see that what I'm trying to get across here is imperative, is first of all, what we do is we set up a result variable. We're going to use this to convey the result. OK, then we check whether or not n is divisible by 3. Then we append fizz if it is. We then check if it's divisible by 5. We append buzz if it is. Now, at the moment, what we've got is a very strong sequential dependency, hugely sequential dependency, basically saying, this had better start in this state, so therefore I can do this, and therefore I can do this. I'm not saying you don't want to do this, but I want to point out something that may be invisible to you in the way that you code. And then we have another dependency. Now we're going to evaluate everything that's gone before. If there's nothing there, then clearly it was neither fizz nor buzz nor FizzBuzz. And the clever thing is we've solved the FizzBuzz problem. The fact that when you hit 15, which is divisible by 3 and 5, it should be FizzBuzz. And because of the ordering, it's just right. Yeah? It's almost. Now, sometimes, I'm saying almost like, clearly for a problem like this, it isn't. But if you look at a legacy code base, actually, some of the things that go on there are almost luck. And what you're doing here is, again, you're running with the state here. You're evaluating. You're not simply evaluating kind of a mental store. Okay. If it's not the result, then the result is the stringified form of the number, then return the result. Okay. Now, if I want to move in something that's a little more functional, then I'm going to use tail returns. I now have to make this case of 15 explicit. But at that level, I no longer need to do checks on any kind of other state. Now, what I mean by tail return is that for everything, there is a mutually exclusive path. I don't do what I consider to be one of those terrible bad habits, which is where everybody says, oh, well, it's OK, there's a return there, and da-da-da-da-da, if it wasn't, you can just do this. It's just like, no, tell the reader. If you're going to tell the reader that this is a mutually exclusive decision structure, then use a mutually exclusive decision structure. Don't say it's a mutually exclusive decision structure because of the interaction of if and return. The idea, and if you've ever wondered why do we indent code, the idea is that I should have some understanding of the function by ignoring or folding away everything that's at this level. Okay? If I fold this away, I can see that there is a four-way decision being made. If I use if, rely on return, if, rely on return, if I fold it away, I have no idea it's a four-way decision. It looks like a series, it looks like a cascade. Okay? So show the reader what you mean. It's about intention. Don't try and be the assembler. You'll be a rubbish assembler. Okay, so if I want to be a little more kind of functional, then what I'm going to say here is actually I should be using expressions, not statements. So therefore, I can combine it as one. One of the reasons I chose Python here is to stop people going, oh, I don't feel good about the conditional expression. Well, first of all, feel good about it. It's OK. You should be able to read it. It's a question mark and a colon. That's not that hard. But this one makes it a little more explicit. Now, that's fairly conventional. Let's try a different approach, because what we're doing here is we're kicking around the properties of the numbers. Let's try a different approach. Let us explore the ranges a little bit, quite literally. Let's take a set-based approach. Between 1 and 100, there's a whole bunch of numbers that are going to correspond to FizzBuzz. There's a whole set of numbers that are fizzes. There's a whole set of numbers that correspond to buzzes. And what I'm going to do here, and there's kind of, you can draw a nice, pretty Venn diagram. Okay? So instead of using the word set, I'm going to use the word range, because that's absolutely fine. And I'm going to do this in steps of 15, and so on. So what I'm going to look at is, if n is in the ones that are FizzBuzz, then I'll take FizzBuzz, thank you very much. Okay? So it's a very, very different way of doing it. Rather than poking and prodding the number, I'm simply saying, look, there's a set of this stuff. Are you in it or are you out of it? And then we will make a decision based on that. Now, if I want to break this one down a little bit, I could start looking at it from a different point of view. What I'm going to do here is I'm going to take another approach. I'm going to say, look, there are fizzes. I've got a list of all the fizzes that I'm going to need. Okay? So in the initial position, I've got to have a dummy because Python's zero counting. But in the proper initial 1 position, it's going to be, there's no fizzes there. 1, there's no fizzes. 2, there's no fizzes. 3, there's a fizz. 4, there's no fizzes. 5, there's no fizzes. 6, there's a fizz. And so on. 15, and so on. Now I'm going to collect all the buzzes that I need. Here are all the fizzes you need. Here are all the buzzes. And then all the numbers. I'll have all the numbers, thank you very much, up to 100, stringified. I'm going to use a map operation. Interestingly enough, the lazy thing does actually carry through here. I've had to explicitly tell Python, please, I'd like this as a list. I'm using Python 3 here. I'd like this as a list, because map doesn't actually map an operation. And you go, what? That's cheating. You called it a map. Why is it not mapping an operation? No. It's telling you about mapping. It's a promise of mapping. What you're actually doing is you're saying, there is a chance, dear Python, I would like to map this operation. If I get round to it, it'll look like this. But it won't evaluate it until you actually need it, until you force its hand, which I've done with list. And indeed, an awful lot of declarative styles are generally about this. They are generally about this idea of saying, I want you to imagine an infinite set of numbers. You don't have to actually do anything. I want you to imagine, and imagine you do the following thing to them. This is actually how Haskell gets around the problem of having side effects and dealing with I/O. It's this really clever sleight of hand that confuses people, monads, but there's a really clever way of doing it. The way you think about it is that it says, I want you to imagine that I were doing I/O. But I'm not doing I/O, so therefore there's no side effects. But imagine that I was going to do this. And if I were to do this, then I would put hello world out onto the console. But because I'm not actually doing it, there's no side effects in this code. And then what you do is you hand it off to the runtime. You outsource it. The runtime has the side effects, but my Haskell program doesn't. Clever, very clever. Haskell programmers, great politicians. So the point here is that we've got all the fizzes we're going to need, all the buzzes we're going to need, and a whole bunch of numbers we're going to need. And then simply what we do is we add them together and make a decision. That's quite a nice approach. I quite like that. OK, let's take that approach. Let's actually explore that. How do I know that these, I've just shown you what, five examples? Yeah, 5 examples. How do I know that they're equivalent? How do I know that I can substitute one for the other and they will all give the same answers? When I say equivalent, I mean semantically equivalent. Obviously, they use different storage and so on. So what I'm going to do here is I'm going to use one of those comprehensions. I'm going to say, right, get me all the FizzBuzzes, up to 100, thank you very much. I've got a list. This is what actually happened. Now, what I'd like is I'm going to establish a set of truths about them, things I would like to know that to be true. For this FizzBuzz implementation to be correct, or for these FizzBuzz implementations to be correct, there are things that must be true about them. Okay, I'm going to create a list of truths, and then I'm going to say they must all be true. Okay, otherwise, clearly, I have a bug. So what we're going to do is we're going to try and explore the properties. Now, it turns out this is where things get a little bit hard. We're kind of wandering into the territory that is sometimes known as property-based testing. And it turns out that it's not that you can't do it. It's just that sometimes, well, you have to be quite thorough. OK, here are the truths. Every result is FizzBuzz, or a decimal string. By the way, if you spot any mistakes, please let me know, because I've stared at this for a while, and I actually found a simplification the other day. I thought, you absolutely need all of these, and I found 2 I didn't. But if you spot any holes or anything that's redundant, let me know. Every result is FizzBuzz, or a decimal string. Every decimal result corresponds to its ordinal position. Every third result contains fizz. Every 5th result contains buzz. I've done this as a kind of programming exercise in class, and a lot of people stop there. They think we're done. No. Nice start. You're halfway there. Every 15th result is FizzBuzz. OK. The ordinal position of every fizz result is divisible by 3. The ordinal position of every buzz result is divisible by 5. The ordinal position of every FizzBuzz result is divisible by 15. So not only is every third a fizz, but there are no other fizzes than those that occur at 3. OK? So you kind of have to come at it from both sides. Given the amount of code that I showed you, this is fairly thorough, and it's quite easy to get wrong. But if you want to be thorough, this is what it's going to look like. Now, with that kind of confidence in mind, that's clearly not Python, as you can tell by the italics. But it turns out that Python's everybody's favorite pseudocode, and actually doesn't take a lot of extra effort. Yes?
I think you need to say that there are 101 results as well. Because if it's just an empty list.
But it's not an empty list. That first line tells you it's not an empty list.
OK. Yeah, true.
Yeah, no, I've definitely kept it on the same, but, yeah, had it come from somewhere else, you're right, I should kick it. Had I made this parameterized, there would have been an extra. And that's a very important point, actually. When people start with, obviously this is a thing that fits on a slide, but when you start scaling this, your natural, hopefully, well, you're at this conference, there'll be natural instincts. Your desire to refactor things and factor things out and avoid duplication will kick in. that actually changes the nature of the game. When you factor it out, suddenly there's a missing truth that we need to say. And you're right about that one. At that point, you have to say, one of my fundamental truths is you just passed me in a list of actuals, but are they all the actuals? Okay? So yes, at that point, by moving some context out, I need to include that. John?
Essentially, had a question. Are you a believer in the Oxford comma? I know it's Bristol.
Am I a believer in the Oxford comma? It exists. Of course I'm a believer in it.
Would you consider it a bug if you fail to use it?
No, it's completely wrong. When people mandate the use of the Oxford comma, they fail to understand English language and its conventions. So I believe in it. I also believe when to use it and when not to use it. And I'm quite happy to correct people who say they're using the Oxford comma. I'm quite happy to correct them when they miss it, but I'm not using it here.
Could I ask you just in the first line, why is it you chose not to put it since you have four equally weighted things? This is to your point.
No, this is because you don't understand English, John. That's a different thing, yeah? It doesn't matter, it's nothing to do with the weighting. The problem is that the English syntax, you're forcing it to do something for which it was not designed to do.
Do that all the time.
Exactly. So there's always a compromise. For every example that you can find supports the Oxford comma, you can find an example that doesn't. What we actually need is brackets in the language, okay? I tried, because then you can say, these are the groupings. Once we've got that, we're done. But otherwise, we end up arguing about commas, and people write songs, and they start campaigns. But I am a believer in its presence and its absence, both of them simultaneously. But I was writing this in conventional English prose rather than standard American book style, which I have also written in. Yeah, done. Okay. Yes?
Sorry, can you just explain how every third result of a fizz is different from the ordinal position of every fizz that uses for a quiz? Because to me it sounds like you're saying the same.
No, I've not said it. Here, every third result contains fizz. But I haven't told you what's in the second result, have I? I haven't told you what's in the fourth. I've only told you that every 3 you should encounter a fizz. I said no statement about the others. I need to make that statement as well. That's why that's there.
How is that different from the ordinal position of every fizz is divisible by 3? It's if and only if.
Yeah. But if you're good with that, I'm going to start scaling things up. Okay? Let's take that idea again. I want to go back to the last implementation I left you with. Well, not exactly. I want to go back to the thinking behind it. I want to bring two ideas together. I want you to imagine all the fizzes. Yes, all of them. And all the buzzes. And you know what? What we're going to do is we're going to combine these to create words. These are all the words you will ever need. All the fizzes, all the buzzes, and all the fizz buzzes. Those are all the ones you'll ever need. And then I'm going to give you all the numbers as well. And then I need to choose, because if I'm going to have all of them, I need to choose when I reach, say, position 17. I need to choose. Do I look for a word? Is there a word, or should I be looking at the number here? And then I will have FizzBuzz. And what does FizzBuzz look like? Well, at this point, the mystery disappears because this is Haskell. What I'm going to do here is I'm going to zip together. I've got all the words and all the numbers, and I'm going to combine them, making a decision. I'm going to turn them into one list, but I'm going to choose from either the words or the numbers. So I need to make a choice. Okay? So now I've got all of that. So let's go and look at how I'm going to get all of the fizzes. I'm going to cycle. There's nothing, there's nothing, there's a fizz. I'm going to cycle. There's nothing, there's nothing, there's nothing, there's nothing, then there's a buzz. How many fizzes do I have here? Infinite. It's just going to cycle off into the sunset and beyond and catch you from behind as well with the buzzes. And then what I'm going to do is I'm going to combine both of those. Plus plus is the concatenation operator. I'm going to combine. That's all the words you're ever going to need, ever. Just don't look at them all at once. Okay? And then the numbers, I'm going to map show is just convert to string. I'm going to convert an infinite number of numbers into strings. Again, don't look at them all at once. Choice, I put this in here because when I first presented this approach, it's based on a version on the Frege website. Frege is a kind of Haskell for the JVM. And I thought, that's a really cool way of doing it, but there's an even better way. The guy had used an if-else. I said, you don't need to use an if-else. You can actually do the whole problem without any conditional logic whatsoever. How do I choose between whether it's a number or an empty string, a number, or a word? You use max. My original version did not use max, and I had different responses to that from people on Twitter. Some going, oh my God, that's such a terrible hack, or oh my God, that's such a terrible hack. You know, that's beautiful and that's ugly, sometimes in the same tweet. So I decided, let me at least capture my intention and say, I'm making a choice, and then it's now an implementation detail that I've chosen max. And if anybody says, yeah, but what if you're running on EBSTIC? You first of all come up with a Haskell compiler on EBSTIC, and then I will answer you, okay? So, oh, and of course, we're just going to take the first 100. What a waste of infinities. How many infinities do we rack up there? There were loads of them. We've got 5 infinities here, and we're going to take the first 100 out of this. Okay, so it's a very elegant but very different way of thinking. What you're doing is, instead of worrying about how am I going to program this up, you're actually saying, well, what is the nature of the problem? Now, sometimes you have to get to the language that you're actually in. I mean, because the point here, as was wonderfully observed by William Morgan a few years back, I love functional programming. It takes smart people who would otherwise be competing with me and turns them into unemployable crazies. You know, it's just like, you know, so either they're unemployable crazies or they're in academia. You know, it's just like these are the only places that it's really the mainstream. In fact, yesterday I was talking to somebody at another conference where they sort of said, okay, so I've got my guys, we're trying to move towards, you know, we've got a C# project, we're trying to move towards some F#, and one of the concerns from one of the developers is, yeah, but what's it going to look like on my CV? I'll be unemployable if I just put F#. And I said, okay, the way you spin that is, you know, is a multi-language .NET project. Now you look cross-skilled, you look really smart, you know, all the rest of it. So the point here is that even with this stuff, it gives you a different way of thinking about it. I did actually, just for a bit of fun, take that Haskell version that I came up with and then come up with a generator-based version in Python using the same principle. So in other words, suddenly it's now employable, so to speak. Okay, so let's look at a different number problem. It's Friday, which reminds me I need to do Word Friday at some point. I run a page on Facebook. I publish an unusual word every Friday and other linguistic and language and wordy stuff the rest of the week, including rules of grammar and Oxford comma stuff, just to let you know. And one of the ones I used a while back, one of the ones I published a while back, was this word that I stumbled across, biquinary coded decimal. That's fantastic. A system of representing numbers based on counting in 5s, with an additional indicator to show whether the count is in the first or second half of the decimal range, i.e. 0 to 4 or 5 to 9. You find this on many abacus systems. Okay? You'll also find it's used on a number of older computers, like Colossus and so on, before everybody sort of said, you know, this trying to pretend it's decimal is really a pain in the backside. Why don't we just reduce everything to 2 bits and be done with it? Yeah? But people spend a lot of time trying to make it like decimal. And of course, one of the most famous ones is the Roman numeral system, which means we're going to look at how do we convert, it's another classic card, how do you convert a number into a Roman numeral? If I give you the number 5.
Intercal.
Yes, that is actually almost a reasonable suggestion. Almost.
Okay,
We're going to get to ISO intercal at some point, aren't we? The imagined ISO intercal, yeah. I is for imaginary. Okay, so there's this interesting question. And this is an interesting coding kata. And, you know, how do we do this conversion? Okay, so if we approach this in an enterprise style, okay, let's reduce the font so we can see everything. Yeah, that pretty much covers it. Normally, by the way, the range that you should be looking to support is 1 to 4,000. That's what's said. Okay, so that's kind of like, okay, fine. I've certainly seen code like that. And
intercal would be shorter.
Well, I think almost anything else would be shorter. Yeah, but this is better. This is a table-driven version. This moves us in the declarative direction. Eventually, people say, you know what? There's 2 parts to this problem. It's not that if I'm taking this very procedurally and very imperatively, what I've done, if you actually go through this, is in fact, let's go to the bigger one. We've got two variables running, number and result. We are modifying both of them at every stage. Okay, we've got two different kinds of control flow, and we've got three, because we are definitely relying on sequence. Okay, we've got a cascade running down, and this kind of does the job. And for some people, they will run fleeing because, oh my God, you're actually modifying one of the parameters to the function as well. And that's sometimes seen as a bit of a no-no. So we're doing all of that. Here, we realize, you know what, there's two things. There's a whole system, there's a regularity. Those if statements are merely while statements that are executed 0 or 1 times. Okay? Let's just generalize. And there's a whole way of regularly sort of looking for the regularity. And there's two parts to it. There's a table, and then there's a bit that runs through the table. There's a kind of like a little kernel that does the logic. Now, what's interesting about the relationship between this and the previous kind of code is I've seen this kind of thing, but obviously not for Roman numeral domains. I've noticed that's not that commercial, is that we end up, in some cases, with this kind of switch statement or if, else, if, and that becomes a hotspot of change, a hotspot of maintenance. People come along and say, oh, you know, there's a slight variation to that rule, or we've added another case, and you kind of get in there, and eventually you end up with the kind of crazy situation. I remember talking to one client many years ago, that we talked about their switch statement. And there was no plural in that, by the way. Actually, that's not the whole truth. There were multiple switch statements. There was the switch statement, and then there were the nested switch statements within it. Okay? But I'm going to use the outer one as a container for all of the sins of the inner ones. But there's two parts to this problem. Here's the table. This is the bit that changes. Our rules and our nice declarative, nice and simple. We know that tables are nice and straightforward and easy because they appear on things like bus timetables. I don't think my parents or members of my family could negotiate an if-else-if structure for a timetable. But if you give them something like a tabular form, what's the time now, the nearest time after, exactly, and what's the one after that, and so on. So this, it turns out that you end up inverting the hotspot of change. Our navigation, our traversal, our lookup remains stable, and it is driven with data. A very simple inversion. Interestingly enough, I did one of those things. Everybody needs to do this at least once, but preferably not much more than once in their career, of leaving behind a piece of code that they tell somebody, by the way, there's a temporary fix in there. After I've left, you should get rid of it at some point. And I did that, and it looked like this. Okay, it was a table. I was very pleased because the version that I'd replaced was this big if else if else if. It was a startup for a server, and I saw this thing, and it just looked really messy, and I thought, no, there's two parts to this problem. Well, let me find the regularity in it, and it turned into this. I was very happy with the solution, but I didn't feel that it was commercially viable, or rather, industrial strength. Anyway, I did speak to my replacement, and I bumped into her about 3 years after I left that company, and she said, oh, we got rid of that. You remember that piece of code you told me about? I said, yeah. She said, oh, we got rid of it just the other week. What, 3 years? And actually, with hindsight, I now realize that that's actually pretty good for this industry. Yeah? The fact that it happened at all is pretty good. Okay, so this is an improvement. We're still changing two variables, but we've got a slightly more regular structure, and we've got a much better localization of change. Okay? It's not a scattering of change over large sequences. It's a much simpler model of change. But there's another solution, and I was made aware of this one by John Jagger, who's hiding in the corner. It came around to my house one day and said, have you come across this approach to doing the Roman numerals problem? Because I got very settled on the tabular approach. And it was a very different approach. It said that basically the fundamentals of the approach is this is not a number problem. It is not a mathematical problem. It's a symbolic problem. It's about symbol manipulation. It turns out that if you look at it like that, oh, yeah, a lot easier. We're just going to replace successively various things. In other words, we take the number, we generalize, we basically say, okay, you've got the number 42, we'll encode that first of all in unary. Okay? We'll do that, and then we will successively transform it through what has become known as a collection pipeline. And it's kind of like, oh, okay, well, that's a single expression. It's highly regular. It is not much more than a table. And it's like, well, that's it. I mean, it's kind of, oh, all of that other discussion was for nothing. It's not a mathematical, it's not a numeric problem, it's not a problem of division or anything like that. There's no decrements and increments or any nonsense like that. Now, this idea of collection pipeline has become increasingly popular to allow people to put dots all over their code and just chain stuff. Chaining has been around for a while, but it's become very much de rigueur with Fluent APIs and so on. And now that Java 8 has them, people have started publishing cheat sheets. I always find it funny that we have this concept of cheat sheet in programming. It's just like, what, you're not doing it properly. You know, you're breaking the rules. Actually, no, use the knowledge. It's there. Use it. This cheat sheet was published by Rebel Labs, or by Zero Turnaround, Rebel Labs. And I came across it, and I looked at it, and I looked at the stream example. And the great thing about these pipelines is it's really easy to see when they're correct and really easy to see when they're wrong. And I looked at this one particularly. Get the unique surnames in uppercase of the first 15 book authors that are 50 years old or over. And I told them, I sort of tweeted, yeah, actually, you know what, you've got that wrong. So they then published a fix. And I said, you've still got that wrong. They haven't changed it since. OK, let's understand what's going on. We've got a bunch of books, got a collection of books in the library. Okay, let's just say that that's some kind of list of books. I'm going to convert that to a stream, in other words, just a sort of iterable thing that I can traverse. And we basically pull it on demand. So we're getting rid of our loops. Now what we're going to do is we're not actually interested in books, we're interested in authors. So I'm going to just go through every element of the stream. I've got a lambda expression here. Like book. When I've got a book, what I'm going to return is the author. So basically, get me all of the authors. Then I want to filter things out. I'm going to filter out all of the authors who are under 50. Okay? Then we're going to truncate that to 15. We're going to limit that to 15. And then what we're going to do is we're simply going to say, well, I'm not actually interested in the authors. I'm interested in their surnames. So please, with all of those authors, take each author, and this is effectively a method reference. So get the surname. Okay? And then for those, shift it to uppercase. Then I want the unique ones, and then I want to convert it to a list. So I've actually got something there. The problem is this doesn't actually do what they asked for, hence my question mark there. Get the unique surnames in uppercase of the first 15 book authors that are 50 years or older. It doesn't quite do that, because it doesn't deal with the case of duplicate authors. Yeah, in some people's bookshelves, if you go through the first 15 books, you'll find that they're by the same person. Now, that's not the same as two authors with the same name. It's the same author. Yeah? So, yeah, that's not quite right. Okay? And we can see that just by reading off it. If you presented this using whiles and ifs, you'd be there picking through and ignoring the loops, trying to figure out what's going on here. This is all very, very simple and directly declared. The version that they replaced it with was also wrong, but we can see why. Okay, I'm going to go and get the authors. I'm going to get all of the authors that are 50 or over, get the surnames, shift to uppercase, and then unique. No, what they've done here is they've got the first 15 unique surnames. That's actually different. The correct version is you need distinct twice. First of all, get all the authors who are in the right age range, and then get the unique authors. Now limit the set of unique authors you have to 15. Now start messing about with surnames and case. And what's nice about this is that it is much, much easier to reason about, much, much easier to see what is going on. It's already there. This rather nice piece by Brandon Rhodes, he sort of talks about this style. He says simple filters can be arbitrarily changed and more easily reused and more robust than almost any other kind of code. He cites an example where Doug McElroy offered a critique and a number of corrections on a piece of literate programming by Donald Knuth. Donald Knuth had, I can't remember what the program was, but he had spent 20 pages of beautifully formatted, I mean, it's Donald Knuth, so it's going to be beautifully formatted, lovingly described Pascal code with English, sort of describing the nature of the algorithm, and Doug McElroy replaced it with about 6 or 7 lines of Unix pipeline. And when I say 6 or 7 lines, I'm not meaning dense lines, I mean one pipe section per line. Yeah? If he had an HD monitor, which he wouldn't have done back then, he would have put it all on one line. Okay? In other words, that 20 pages, poof, just disappeared. You just need the right frame of looking, the right way of looking at the problem. Okay, so given that, let's go back to these words. Let's go back and find a different word. Paraskevidekatriophobia. Yeah, you can ask me to say that again later in the bar after I've had a couple of drinks, and I might not get it right. Fear of Friday the 13th. Okay, it's obviously one of those wonderfully contrived words, but that's true of most words. And for those of you who actually are interested in poking and prodding and making fun of any friends they have who have this fear, if anybody tells you, oh yeah, it goes back to the Templars or it goes back 2,000 years, no, it actually turns out to be very recent as a kind of superstition. And yeah, there's a whole bunch of other stuff and me being cynical there. However, let's do this as a pipeline solution. So I wasn't originally going to put this in the talk, but I did it at another talk this week, and I put up a piece of code, and Chris Oldwood pointed out that there was a simplification that I completely overlooked, because I hadn't looked at the code in a while. And I thought, oh, actually, now that he mentions it, there's another simplification I can do, and it actually ended up even nicer. But I'm not suggesting this is the most efficient way of looking at it, but it does show you that you can do anything. You can do and, you can do sequences of mathematical operations just by pipeline. You can really push this a little bit too far sometimes. Get yourself a sequence of days, include only the 13th of the month, include only the Fridays. Okay? This is turning sets into streams, which I believe that Thomas Guest did an absolutely brilliant piece on a few years back. And you can do it in PowerShell. Yeah? I'll have next 500, I'll have 500, please. I'll take the days, I will add them, I'll filter out anything that's not 13, filter out anything that's not Friday, and I'll take the head of that list. Thank you very much. And we are done. That's the next Friday the 13th, which is in May, I believe, but if you care about that kind of thing. So you can take this quite a long way. How far can you take it? Well, it turns out once you've started messing about with this, it becomes very attractive. You realize, actually, I can do Roman numerals shell script style. Let's take 42. That should come out like that. Yeah, it does. What I'm going to do here is my unary generator, this is bash, my unary generator is I'll have 100 spaces, please, and then I will transpose every space to an I, so now I've got my unary count, and then I'll just pipe it into set, and then do a successive series of transformations. Now, to really push the pipeline point home and also get rid of any CPU we might have had left over, we can actually do these as individual pipe stages. I'm not recommending this, but it's this simple idea of the composability of these things, these simple sections, this idea of reasoning. It becomes, there's an extra step that you have to know the language, the regexes, and so on, but once you've got that, everything else just fits together, and it's easier than Lego at this level. Whereas when we look back at the first version, the if version, if and while version, it gets messy. Now, this is all very well, but obviously we want to talk a little bit more about things of substance, other things in computer science. We want to talk about objects. Here's a stack of books about objects, although they all seem to be about psychoanalysis. It turns out everybody in every discipline is obsessed with objects. This is mostly Freudian nonsense, but there's a nice stack of books here. Oh, that's what we want, stack. That's what we're talking about. It's a stack. Let's talk about stacks. Everybody loves stacks, especially undo lists. Those are very useful. Okay, so how do we characterize a stack? I'm going to characterize a stack very, very simply here. I want to understand how I can declaratively approach understanding a stack. Instead of obsessing over whether the internal implementation should be a vector or a deck or something else, I'm just going to focus on how am I going to use it. Right, first of all, it's got a set of operations, push, pop, depth, and top. Okay, we'll take that. Okay, now, how do I think about using it? Well, I think of it in abstract data type terms. I might say, well, there's a bunch of operations that we can elaborate this. A stack of T, you can push a T, you can pop. This is going to be a strict command query separation, so you can pop, but there's no result. If you wanted that result, you have to go and ask first, top. So this is a little more STL-like in that sense. And we can ask the depth. Okay, so that seems not necessarily unreasonable. But obviously here, just the names are suggestive. There's no, what we're missing is a binding contract. So this idea, an interface is a contract to deliver a certain amount of service. The idea of an interface as a contract goes back quite a long way. I found the earliest reference that I've been able to find concretely for this wording is Butler-Lamson, his for computer system design. So that's the early 1980s. That paper is really worth a read every now and then. It's surprisingly fresh. An interface is a contract to deliver a certain amount of service. Then Butler-Lamson shows, blows it by showing a remarkable amount of optimism. Clients of the interface depend on upon the contract. Yeah, that's good. I like that. Which is usually documented in the interface specification. Oh, you work in a research environment. Of course you do. Usually, honestly. Yeah, which optimistically is documented. There you go. We discovered that when it comes to documentation, that slide I showed earlier, lazy evaluation, yeah. But we want a reasonably rigorous approach to this. Let's say we do try and document this. How are we going to go and do this? Well, the term contract was popularized more greatly by Bertrand Meyer in the late 80s onwards. But object-oriented software construction, he described the Eiffel programming language and a particular worldview of object-oriented programming. And it was kind of influential at the time, but when I look back at this book, it was, I think the phrase I would use is quite deeply flawed in a number of ways. Mostly it showed you how to do structured programming with abstract data types, and also what happens when multiple inheritance runs wild and is advocated strongly. Yeah, it didn't really deal with what I would recognize as being sort of typical object-oriented structure. But he helped popularize certain ideas, including this idea of design by contract, the idea of using pre and post conditions on a per method basis. So let's go and have a look at that and see what's going to go on for stack here. Okay, so given that before, let's give ourselves some convenient localized captures. Given before is depth, the post condition is, after a push, that the depth is whatever it was before plus 1. And the top is equal to the item that you've just pushed in. That seems not unreasonable. Pop. Given that before is the depth and the precondition is you must have something to pop. Okay, there must be more than 0 elements there. The post condition is the depth has become whatever it was before minus 1. Again, this is not a false statement. It seems entirely reasonable. Depth. Given the result is equal to the depth, then the depth is going to be not negative. So I've defined I've narrowed it down to an infinite number of numbers. Great, that's really helping. As a contract, I would say this is almost useless at this point. What is the depth? Oh, somewhere between 0 and int max. Yeah, thank goodness for implementations, otherwise we'd have an infinite number to look through. And what is the top value? I have no idea, but you can only ask this question if the depth is greater than 0. Okay, this is the pre and post condition model. A lot of people get very excited about this model. I got very excited about it last century, and then I actually tried to use it, and I tried to use it as documentation, and it turns out you can't actually use it for anything that is not a sort of a simple algorithmic model or a very comprehensive or rather over-bloated object interface. I could solve this by having a whole load of other stuff. I could make my interface a lot larger, so I could now talk about my previous state, because you'll notice that our statements are actually, although they're not false, they are trivial. I mean, these are the most trivial. You know, the depth is greater than or equal to 0. The top, well, you can ask this question if the depth is greater than 0, but I can't tell you anything about the answer. I have no history sensitivity in this interface. Unless you tell me how many pushes, how many pops, I can't tell you the depth. Unless you tell me what you pushed and what you popped, I cannot tell you the depth. Unless you give me access to all of the elements, which is certainly reasonable for a number of collection-like structures, but in this particular case, we've gone for a very strict stack interpretation. It turns out that for certain interfaces, you cannot use this to say anything other than trivial statements. We've also not said anything about the fact that when we've pushed, that all the other items remain as they were. So, although everything we have said is true, it's only a very small part of the truth. And so there's not a lot there. Yeah? A better way of looking at this is to go for another old book that has a red bar on the left-hand side, good old Prentice Hall, and sort of look at it as kind of being a more sort of executional process-based problem. There's a calculus for this, CSP. Now, I'm not going to do CSP. I'm just going to sort of nick some ideas from it. There's a terminology, alphabet, although we might call it the vocabulary. Vocabulary might be a better term. What can you talk about with a stack? Well, I can talk about push, pop, depth, and top. OK. What are the possible interactions you might have with a stack? So what are all the legal sequences legal sequences of operations you could ever engage in with the stack? So that's the trace, or the set of traces. And you can do nothing with the stack. I give you a stack, you ignore it. Okay? You can take a stack, you can push it and never look at it again. You can take a stack, you can ask for its depth. You can take a stack, you can push it, you can pop it, you can push it, you can ask for the top. You can push it, you can ask for its depth. You can push and you can push. Keep going. You could be here for a very long time. But this is the great thing, ... It's fantastic, isn't it? It's just like, yeah, you get the idea. But what we've done here is what we're doing is we are defining the legal set of possibilities. Now, normally we try and reduce, yes, John?
I'm just asking so I understand. You have an empty set. You can still ask its depth, right?
That's there. Let me clarify. This is a set of all the possible interactions you could ever have with a new stack. So here I've just said, thanks for the new stack, I'm not going to use it.
So where do I find the part where I say, thanks for the new stack, but I'd like to know your depth?
Second line to the right.
That one.
But that is pushing them.
No. These are, that's a sequence of interaction. It's a set of sequences. So the left-hand angle bracket is, I've got a new stack. The right-hand angle bracket is, I'm no longer using it.
Okay, it sounds like I just don't understand it. That's fine. We'll talk more.
Okay, this is parallel universes. That makes it much more comprehensible. Okay, what we've got is there's a universe where I do nothing with it. There's a universe where I only push it. There's a universe where I only ask its depth. So these are all the possible future histories. Got it? Yeah.
Yes.
Absolutely. So this is probably a great way to keep lots of people employed. How are you doing with that specification? Well, you know, we haven't quite got the infinite set of interactions, but we're getting some idea of, well, what we do is we normally try and factor out some kind of regularity, some kind of grammar, okay? Tony Hoare used obviously a more mathematical notation, but we can quite easily capture this as a Hurrell state chart. And we can say, look, you got a new stack. It can be empty or non-empty, okay? If you ask the depth on an empty stack, it remains empty, and that's a perfectly legal operation. If you push on an empty stack, you get a non-empty stack. If you ask for it, you can ask for its depth, it remains non-empty. You can ask for its top, it remains non-empty. Notice top is not a legal operation. The possibility of asking for top on an empty stack is not allowed. It's outside our definition. In other words, it's undefined. We can push onto that. We can pop. If the depth is greater than 1, we remain non-empty. If we pop and the depth was 1, we become empty. That will generate, so this is going to save a lot of work, okay? The previous slide goes on for forever. This one, we've now generated all the possibilities. Now, how am I going to talk about this? How am I going to bind this as a contract? That's a contractual relationship. I can turn it into words, but I prefer an executable form. And the pre- and post-condition model is not quite going to cut it in this one, so I'm going to use a different way. So I've got this as a JUnit test. Interesting. I actually originally started this because I made some Twitter comment a while back that I was very unhappy that every time I saw people trying to present unit testing frameworks, and they used the stack example, they always ended up with rubbish stacks, or rather rubbish testing code. And there's the original BDD book shows you how not to test a stack. In other words, you look at it and you say, well, you're exercising the framework, but actually that's not a good set of tests. So what does a good set of tests? And I think this is fairly reasonable. I can change a couple of the names, but I think it's sort of in terms of its structure, I'll just reformat it a bit. So we've got the nesting and bring that out. So a stack spec, a new stack has no depth, a new stack has no top. I might want to change that to a new stack throws when you ask for its top. An empty stack throws when popped. An empty stack acquires depth by retaining a pushed item as its top. A non-empty stack becomes deeper by retaining a pushed item as its top. A non-empty stack, on popping, reveals tops in reverse order of pushing. So we managed to get all the historical stuff in there, the history traces. So we've kind of captured pretty much everything that is being said there, but now in an executable form. So you can actually check one against the other and do this reality check. Now this does lead to the interesting point that the testing style, and I still find it's relevant to say these things, if you want a testing style that is very communicative, very literate in this sense, we end up using a style that is focused on a declaration of intent. Or to be precise, we're going to be very logical about how we do this. This is one of the books I learned logic from. People don't use fonts like this anymore. I think that's disappointing. Comic Sans has replaced the kind of, it's become the comedy font, but I like that font, you know? It doesn't say logic to me, so to speak. It says a certain playfulness on the part of the publisher, you know? But the whole idea is what we're doing, whatever we're trying to do, the idea is here is it's a proposition. We're trying to tell people, here is a thing. This is how things are, okay? Or how we hope they are. That's the whole point of a test, is that you kind of try and have your aspirations meet the road. And so there's this very simple idea. And so that tells you your naming style. If you're going to do this stuff and you're going to have named tests, structure your tests so they reflect propositions, truths about specific examples or general cases. And therefore, that also tells you the kind of part of speech that you're kind of expecting. So things that can be said to be true or false. Now, if we want to look at another issue, though, so although we've sort of said logic, surely that's the pre- and post-condition stuff, I'm saying yes, it is, but there's a limitation there. The thinking is still very useful. Another area where pre- and post-conditions struggle is with the problem of concurrency. I came across this tweet recently. If you don't know Guns N' Roses' Paradise City, it's not going to make any sense to you whatsoever, but I love that. Take me down to Concurrency, where green pretty is grass, the girls and are. And it turns out that the whole question of pre- and post-conditions kind of becomes a little bit weird when you start dealing with concurrency. The precondition to calling this function is that something is true. Right, when was that supposed to be true? Yeah, because it turns out in a concurrent program, the clue is in the word concurrency, things go on. It was true when I started, but it wasn't true when I finished. When I started executing the expression, that truth ceased to be true. Okay, and you could try and think, well, maybe I make the condition itself a blocking condition. That's potentially useful, but also potentially problematic. And half the reason we get ourselves into this state is it turns out that pre- and post-conditions are rubbish for re-entrancy. Not just concurrency, but actually callbacks and things like that, any form of re-entrancy. They don't really cover the ground very well. But while we're on the subject of concurrency, we do tend to overcomplicate things. So I drew this up on a flip chart a few years ago running a workshop and decided I would put it on a slide, so I now seem to use the slide everywhere. You know, quadrant diagrams, everybody understands a quadrant diagram. And this quadrant diagram, I'm going to sort of really emphasize what we have ended up doing wrong. I'll put it in red, and I'll put a big quadrant mark here. This is called the synchronization quadrant. We have divided the universe into 4, okay? And normally with any quadrant diagram, there's either one quadrant that's very, very good or one quadrant that's very, very bad, okay? And so we're not taxing anybody's reasoning here. We've only got 4 things that something can possibly be, and then one is either very much where we do want to be or very much where we don't want to be. The red here tells you that you probably don't want to be there. Nature's color for danger, okay? It turns out that we took a bit of a wrong path in the 1990s when it came to offering people concurrency mechanisms. I'm not saying that we didn't know this before, we knew this before, it's just that 1990s is where it kind of got popular. It kind of started happening. It kind of meant that people were starting to talk about this as if it was something that they could actually use in their applications. And it started appearing in languages and libraries and so on. So the mutability axis, you can either change, you've got state. It can either be changed or not changed. You can share state or not share it. So the sharing axis, you can share state between threads or not share it. Very, very simple. So that gives us 4 kinds of code that we can have. It turns out there's only one quadrant where you have problems. And this is where most code lives, okay? And people insist on putting their code in there. What they do is they set out and they say, right, I'm going to have an assumption here. Or they don't know they have an assumption. You don't normally realize an assumption is something you hold until it's contradicted. Okay, so there's this idea. People say, right, okay, so what are we going to need? We're going to need locks. Why do you need locks? Because we're going to have threads. Yeah, but you haven't told me why you need locks yet. Well, because we're going to have threads. Okay, you haven't told me why I need locks. You've told me why that you're going to use threads. Well, because data might be shared between threads. Yeah, you still haven't told me why you need locks. They're looking at you like you're a complete idiot at this point. but stick with it. Because eventually they'll say something like, well, you know, what if one thread changes something while another thread's looking at it? Look shocked. I did this once with a client. Look shocked. You're changing it? Good God, who told you you could do that? What stupid idea is that? And why did you tell me last? The most important thing is the one thing you didn't tell me. You told me one of the most trivial things, first of all, we're using threads. That's not interesting. We are sharing mutable state between threads. Oh, can I just suggest, don't? It turns out your life becomes a lot simpler. If you live out here and basically say, hey, I've got mutable state, but you can't see it, well, not my problem. Okay, that's great. We don't have to synchronize on anything. Synchronization, the word synchronization is there because you are synchronizing changes between things. If you don't have a between, there's no problem. And if you don't change, well, that's the other half there. It's not changing. Okay, do we need to lock it? No. But I've seen some great code where people have, you know, they have methods that are, so this is in Java code, so methods that were synchronized and they didn't operate on any object state, just their arguments, because they've just gone and put synchronized everywhere. I've seen the equivalent C++ code where I've seen people put locks everywhere, including the constructors. When you are not being shared, or rather, if you are, really just delete that code. That singleton I showed on slide 2, go and have a drink of that. You will feel much better afterwards. The problem is, this is a path dependency. We've got ourselves into this problem by thinking in a very imperative thing. We think that state is a thing to be changed rather than a thing to be declared. Here is a value. There it is. So let's do something slightly different. This is just one of the best article titles. Communications of the ACM, January this year. Immutability changes everything. Well done, Pat Helen. That is just a superb title. So let's reason about this one a little more clearly. Michael Feathers made a very good observation a few years back. Object orientation makes code understandable by encapsulating moving parts. Functional programming makes code understandable by minimizing moving parts. And this is true of many declarative approaches. Now, I want to approach the stack problem. I want to revisit the stack problem. Say, yeah, that's all very well, but how are we going to get a concurrent stack that is, you know, I don't know, that's safe and is kind of immutable and does this kind of cheating, well, kind of cheating thing that I sort of described earlier. So many years ago, I got myself a master's degree, and my thesis was on actor-based computing, and it was based on this language, an actor-based concurrent language. And perhaps the best way of understanding it is I'll borrow a quote from Andre. Multi-threading is just one damn thing after, before, or simultaneous with another. It's brilliant. Captures it perfectly. Actor-based concurrency is just one damn message after another. That's it. You have localized sequential reasoning. When you are within an actor, it's a kind of object, but actually it's also a kind of function. It's kind of both. What you're doing is you're simply responding to requests. And you're responding to them, you receive them, you respond to them. That's it. You don't perceive other threads. You are always messaging, and it's always asynchronous. So you're not blocking. Blocking is a state dependency. It's an imperative dependency. Now, that sounds a bit challenging for our stack, so I'm going to reframe the stack a little bit. I'm going to simplify it and mess about with it. Okay, so let's go back to our stack. I'm going to change its alphabet. I'm going to change it so that what we're talking about is I'm going to simplify it. I'm going to get rid of the top operation. I'm going to combine, simplify it down to basically push and pop. Now, you'll notice that the alphabet there also includes popped and empty. I've not made a distinction in terms of direction, but what I'm doing here is I'm saying if I'm going to interact with a stack, this is all the conversation we can have. I can ask it to push and pop, and it can tell me I'm empty, or here's the popped value you asked for. Okay? So this is the whole conversation we have. I'm really going to narrow this one down. And from a trace point of view, that basically means we can do nothing. We can push on it. We can ask it to pop, and it will tell us that it is empty. We can push and push. We can ask to push. We can ask to pop, and it will tell us that it popped. In other words, you'll see that some of these get responses. Okay? So it's a different alphabet. I'm not showing you who's saying things. I'm requesting push, but it's telling me. I'm requesting pop. It's telling me popped. But we capture it a little bit like this, and I'll simplify it as the two operations you can do on a stack are push and pop, and the signals or events you get out of it are popped and empty. We look at it like that. It turns out if we use something like Erlang, we can actually have a very elegant way of describing the stack just purely in terms of functions. So here's a function. This is a function called empty. It's the name of that state. Empty is going to wait and wait to receive. It can receive one of two things. It can receive a push request or a pop request. If it receives a push request, there is a variable, as it were, a value called top. If it receives a pop request, you give it a return address. Yeah? I would like you to pop, send the result to me, please. Okay? And then we end our receive. This is a function. And then we tail call empty. The best way to read this, and this is used in CSP, it's used in pure actor models. The simplest way of looking at that phrase is, rather than call empty, become empty. Or remain empty in this case, because we started empty. The tail call, don't worry, you're not going to run out of stack while implementing the stack. It's optimized away. In fact, I really hate that term in some languages, tail call optimization. In some languages, it's not an optimization. If you don't have it, it blows up. It's the difference between a correct program and an incorrect program. That is not an optimization. It's actually a necessary feature. So here it's a necessary feature. So we start off empty. We do all of this. If we can't reach that point, we're still empty. Continue being empty. There's no while loop here. OK, let's look at what happens when you get popped in the empty state. I receive pop, there's my return. Well, I've got nothing to offer you. I'm empty. So you return, you just say, I'm empty. That's just a symbol. It's like a literal, effectively. So I'm just going to say, yeah, return empty. And remain empty. If, on the other hand, it's a push request, oh, OK, that's different. If it's a push request and you give me a value, top, then I will become non-empty with that value. Here's non-empty. It's also a function. These functions represent states. I will receive, so I've got the value, that's my local, that's a parameter, so hence local, it's local to this function. I also can receive push and pop requests. If I receive a pop request, then I send to the return address, here's the popped value, and that would be the value that I currently have. And then I return from this to go back to emptiness. If I receive a push, then I become even more non-empty, but with a new value. If that one pops, it returns, and I remain non-empty with this value. It's a really simple model when you get your head around it. It might be too early in the day to get your head around it if you've never seen this kind of thing before. And by that I mean maybe you need a drink, and it does actually become fluid and clear and all kinds of great stuff. But it's a very elegant model. And so here's an example of interaction. So what I'm going to do is I'm going to I put this in a module stack. I'm going to say, right, I want to spawn a new process. I'm going to call it stack. I'm going to take it from the module stack. I only need the function empty. I'm going to start off empty, and I've got no arguments to that function. Okay, that's a list of arguments provided. The next thing I'm going to do is I'm going to say, right, I'm going to ask you to pop. I'm going to tell the stack, I'm going to request a pop of it. I'm going to give it my address. It returns me an empty. Next thing is I'm going to push 42. Then I'm going to pop. From that, it gives me pop 42. I'm going to push 20, push 16. Then I'm going to pop, get 16, and then pop again, and I get back 20. So this is the clever way of doing a stack. This is one of those things like, there's no side effects here, except for the fact that I can see it on the screen. But remember, that's not part of your code. It's a very declarative thing. You can rephrase it as now become. Rather than keep counters and do various things, you've got a very simple way of structuring this. Now, of course, that's not going to be available in a lot of languages, but the style of thinking is something that pushes you to a very different model of threading or very different model of concurrency. It's very elegant and very minimal. So let's look at some Latin. Because this idea of thinking about requirements, how do we talk about requirements? I couldn't be bothered to come up with some requirements, and quite frankly, the classic lorem ipsum is probably about as coherent as most requirements documents I've ever encountered. So I don't think there's any difference, and there's no love lost. So once upon a time, people wrote requirements in just big blocks of text and big Victorian or Victorian novels or Latin scrolls. And then somebody came along and said, oh, you know what, use cases. So they came along with use cases. And these use cases really weren't that comprehensible. And then people started structuring use cases, because all it turned into was a shopping list. People started structuring the use cases, and this is where it started getting interesting, because people did stuff like, OK, here's a trigger for this use case. Here's the precondition. Here's a sequence of things that you then do. Here's the postcondition. And sometimes people would vary which way around they put the precondition and trigger. Again, I didn't find this that useful until I one day saw this approach. Suddenly it became useful. You tell me what needs to be true before we engage in this activity. You tell me what the trigger for the activity was. You tell me what must be true afterwards. And here's a bunch of really boring detail you can ignore. So we did. And then this became my favorite use case form. You just don't bother with the sequence. You really focus on the truths, the declarative truths. Rather than programming procedurally very badly in English and in Word, what you ended up with was a clear statement of what must be true before we engage in this activity, what is the cause of this activity, and what must be the result, a necessary truth that is a testable truth afterwards. And then everybody got very excited about user stories, and then it got reinvented, just using different words. Nothing new under the sun. Jason Gorman observed last year, given when then is what we call a Hoare triple. This is how you reason about state change, but indeed how you reason about many other things in the kind of classic formal methods approach. Here is a thing that must be true before this executes correctly. Without this, the behavior of this is undefined. Okay? Here is a thing that must be true afterwards. That's your postcondition. So we kind of knew all of this, but we're coming at it from a different angle. The pre- and postcondition model is very, very useful. It's just not always enough in certain cases. But as a general model of verbal and informal reasoning, it's always good. Yes?
Could you explain when? I understand pre and post, but I don't understand when.
That would be a trigger. In this particular case, the idea is that when something is executed, when there is a trigger, an external event, when a timer expires, for example. And that would say, rather than there being a truth that the timer has expired, which is kind of playing fast and loose with mood in English, you're actually saying, here is a state, the stack is empty. When somebody asks to push, then we get that. A thing happened, we were in a state, a thing happened, that's the when, that's the transition.
When somebody calls me a method on a class.
Effectively, you can look at that as the when, yeah. So all of this relates to logic, and it turns out that people thought that we were all very logical. George Boole, for example, he codified propositional calculus, put it in a book, which these days we call the laws of thought, but in true Victorian fashion was more formally called an investigation of the laws of thought on which are founded the mathematical theories of logic and probabilities. Had this been written in the 21st century, it had probably been thought in 21 days or thought distilled. And there was this very simple Victorian idea, because obviously the whole universe had been understood in deep mechanical form, and the Newtonian thinking reigned supreme. We understand everything, and the human mind is open and amenable to reasoning. And the reason that people are irrational is because of society and education. Well, yeah. So I'm going to pick on an example related to one I looked at last year. So this is Q-sort taken from the C library. Let's try and do a pre- and post-condition thing, because it turns out, yeah, right. What's the precondition? Q-sort takes a pointer to a base that is untyped. Because it's trying to be generic and C, it's going to struggle. So we're going to say how many elements and how big are the elements. So we're going to talk about this in terms of memory. And we're going to pass in a function pointer that is going to do a comparison. And the idea is that then it's going to sort it in some way, well, using some mechanics. What's the precondition? That's really hard to state, like really hard to state. Base is a valid pointer. How do I state that in C? Trick question. You can't. There's no way to say this. So within the frame of Q-sort, there is no way to describe the necessary truths for its execution. Okay? I can say that it should be non-null. That's trivial. I mean, that's certainly got to be the case. But here, if I say it must be a valid pointer to element count times element size of memory, such that when you execute compare on it, the type conversions inside compare will yield objects that don't cause undefined behavior. Yeah, that's easy. Just write that. I understand what you're saying. Just could you turn that into C and put those? Yeah. It turns out the postcondition, people think, oh, okay, thank goodness, we've got past all that nastiness. Postcondition, whenever I ask anybody, what's the postcondition of sort, and I do this in classes, most people, occasionally there's an exception, most people Give me a very simple response. It's sorted. This is necessary. It's a true statement, but it's not sufficient. What everybody forgets is it's sorted and it's a permutation of all the original elements. You've got a conservation of elements. And everybody, oh yeah, I knew that. Yeah, but you didn't say it. And guess what? That's the bit that I'm trying to highlight. It's sometimes really hard. Even if you are in a situation, something like sort is a classical example of something you should be able to write pre- and post-conditions for.
There is a precondition that those void stars are the same.
No.
That doesn't work, right? If that function interprets those void stars as different to the size of the element.
Oh yeah, but the thing is, I gave you the precondition before. The problem is I can't state it in C. I can't state it in a way that is executable. In other words, I have to go outside C to state it. Just as for the stack with the pre and post conditions, it was not a question of definers, but to really say everything about it, the fact that the values that were there before have moved, I have to go outside the vocabulary of the thing. So this is the thing, is the abstraction. At this level, I cannot describe the valid precondition. And even when I come to do the postcondition, the chances I've got a blind spot, because it turns out that we're not very good at being logical. As was observed in this rather good book by Gary Marcus, The Haphazard Evolution of the Human Mind, Kluge, are human beings noble in reason and infinite in faculty, as William Shakespeare famously wrote? Perfect in God's image, as some biblical scholars have asserted? Hardly. It turns out we're rubbish at this. So let me look at another example. Kind of close with the, one of my other favorites is leap year. Just in case you're worried about the scope of this, I'm using a proleptic Gregorian calendar. If you don't know what that means that you can't criticize any of the logic. And if you were going to criticize any of the logic, you'll discover you can't criticize any of the logic. So we're done. Is a year a leap year? OK, that precondition is it's a year. Fine, that's trivial. My question here is, what's the postcondition? Okay, what's the postcondition? So I had this discussion with somebody who was sort of saying, oh, we don't want to do unit testing because you just need pre and post conditions. And I said, well, pre and post conditions will just sit there. How will I know the pre and post conditions are going to be correct? Well, because they will trigger something in the runtime. And I said, well, actually, some of the preconditions cannot be stated cleanly, if at all. And some of those post conditions may be costly. It may turn out that you've got what you hope is a logarithmic function, but the only way to assert its postcondition is to do a linear operation. So you just blew the operational part of the contract out of the water. But that sometimes we end up with another problem. The problem of defining what a leap year is actually defining its whole postcondition. That's all it is. This is the postcondition. Given that result is leap year of year, the result must be equivalent to that calculation. But that's the bit that people are struggling with, because guess what? That's the implementation. In other words, the postcondition is identical. So I actually have seen this when somebody was doing it. They copy and pasted the thing. It's just like, yeah, what level of correctness have we just assumed there? We've assumed that the copy and paste of the editor is correct. And there's more chance that that is correct than the code that you copied. Yeah? So we have this problem here. And then people say, right, we're going to test that truth. We're going to call the thing test is leap year. That's not a great name. This is the other popular one. Yeah, unless you're prepared to write that this thing does not work, then this is a content-free statement. So what we're really after is a very simple idea. This is what we want from a very kind of communication-based style of testing. Tests serve many, many roles, but I want to emphasize a communication-based aspect. I want to get back to this idea of declarative. The idea that my test should offer me an expression of intent. If this is a test about code, then I should be talking about intention with respect to code usage, and I should use data that is somehow real or useful. OK, so let's try that. OK, so so this is in Python, and here's a very simple, lightweight approach. I've just strip out all the rest of the bits and pieces. Years not divisible by 4 are not leap years. Years divisible by 4 but not by 100 are leap years. Years divisible by 100 but not by 400 are not leap years. Years divisible by 400 are leap years. This is effectively the equivalence partitioning of the whole domain. There are 4 kinds of years, effectively, not 2, not leap years and non-leap years. You've got 2 different kinds of leap years and 2 different kinds of non-leap years. Now, these are propositions. We've just stated them, and this is either true or not. For a failing implementation, then one or more of these will not be true. And so it's this idea of propositional statements. Just as a point, that's not a standard Python testing framework. There you go. That's all that's needed for that. Let's go back to this. Yes?
More quickly, that's really a year.
Ah, right, we're going to get to this because I've made a statement, but I've only given you a single exemplar. Because what I need is a little bit more than this. There's more variation here. And the question is, how much variation do you want to take on? If you're about to get on an aircraft at some point in the next few days, you really hope the people who wrote the software for that aircraft really used a lot of data, rather than, oh, we just got a single example, land, it's a simple case of, we tested the landing software once in one scenario. The wind speed was 0, and it all seemed good. You really need, these are the axes of variation, okay? For these kinds of tests, how do I express intention? Naming and grouping and nesting. These are the mechanisms available to me in a language and within a framework, and I can choose this or have it imposed upon me by a particular framework. Of code usage, show the code being used. This is really important because I find a lot of people overfactor their test to the point that the test tests something that I can't see. And it was, would be really helpful to see the code that's actually being used. You've now factored out the code. And I haven't quite seen it as the method being called the code, but not far off. With respect to data, now, we have 2 questions. One exemplar or many, explicit or generated. So now I started off, as you said, with a single one. Now, I might try and go in here and hard code this, because it's such a simple thing. I could do multiple examples like that. I could do it like that. I could ramp up to a nice little loop there. Oh, and a loop with an if. The problem now is that we've ended up with tests that are actually harder to read than the original code. And so although these may be doing the right thing, it's not entirely obvious that they are the right thing. The probability of having a defect in your test has now increased. So we clearly need a different way of looking at this. And so I've just sort of beefed up the testing framework ever such a little bit. So now I'm going to work with explicit data. So now I'm going to parameterize the test. I don't want the loops. I'm tired of writing loops. I don't want loops in the code to test. My goal is not to loop around a bunch of years. My goal is, here's a bunch of years. This statement is something I want to demonstrate some level of truth of. That's what I want to see. And I understand the data-driven approach, so I'm going to write it like that, or I can write it like that. We can see the parameterization is much, much clearer. It's just like, OK, 2016, 1984, 4. These are not sitting in an array somewhere. There's no loop mechanics. It's just like, yep, those are leap years. I'm good with that. I might start getting a little bit fancy here. What I'd like is every 400 years from 400 to 2400, thank you very much. And I might just be straining it a little bit if I do this. Every 100 years with the exception of every 400. There. That one's pushing it a little bit, but there's a couple of other ways of generating that and organizing that. But I'll leave that as an exercise for the bar. What we've got here is, as it were, a clearer idea of what we mean by the intent and how we've organized this, and we've sort of said, OK, what I'm after here is here are the things, here are the concrete values, but the statement is unchanged. I still want to say that years not divisible by 4 are not leap years. I originally used 1 example. Now I've got 3. Now I've got 100. Now I've got many more. The point there is that that's an axis of variation that shouldn't have to express itself in control flow, because verbally I wouldn't use control flow. That's a nonsense. And it actually hides what's going on. So that's what we're after. So to bring it back away from testing to the bigger picture, intention is what we're after. And specifically, declaration of intent. And we're not very good at this. Often it seems that our intent is to create variables and modify them. What does this program do? It's got a lot of integers and it changes them. Sometimes that's what it feels like. Our system's special. We use strings as well. Oh, it's a stringly type system. Great. So we need to get beyond that. And these styles of thinking can either be executed directly, as it were, into code, or at least inform how we structure it and the world around it. Thank you very much.